In this video, we will find the global maximum and global minimum of a function on a closed and bounded region of the plane. So here we're given a function of two variables and a region that we're calling D, which is the closed half disk of radius 4. So we're saying it's the set of points, so that x squared plus y squared is less than or equal to 16, meaning it's within the disk of radius 4, and y is greater than or equal to 0. So it's this region, the top half of this disk. So let's outline what we're going to do first. So what is our process? First, we will find interior critical points, meaning critical points that are inside the region. And two, we'll parameterize the boundary which, depending on the region in question, may have to be broken into pieces. Like in this one, we'll have to break the boundary into two pieces, the bottom horizontal edge and the top circular edge. Step 3, we will plug our parameterization into the original function with the purpose of doing this is to get a function of one variable. And the reason we do that is because in step 4 we will use techniques that we learned in Calc 1 to find critical points of this one variable function. And then in the end, we'll take all the critical points that we found in step 1 and step 4, throw them all together in a big list, and just evaluate the function at all those points and see what the biggest and the smallest values that we get are. So let's go ahead and get started. Step 1, to find critical points, we need the gradient vector. So we just take partial derivatives. So the x derivative is just 2x, and the y derivative is 16y minus 32, which we can factor out at 2 and write it like this. So we see we get one critical point. So there's one interior critical point, which is where x is 0 and y is 2. Okay, that's it for step 1. Step 2, we'll parameterize the boundary. So I'm going to color code this. So first, let's do this bottom edge, which I'll color blue. And I'll parameterize it as R1. So an easy way to parameterize this is just t comma 0, and of course t runs from -4 to 4 here. Now, we also need to parameterize the top, the circular arc. Now, one easy way to do that would be to do it like this. parameterize it with x being the parameter, and then solve for y in the equation of the circle to get something like this. But, as it turns out, it'll be slightly trickier in the later steps if we do it that way, so I'm instead going to choose to do it a different way. I'm going to break the top circular arc into two pieces, the left and the right. So the left one I'm going to color red, and parameterize that as what I'll call R2. I'm going to parameterize it with y being the parameter. And so if we solve, we'll get something like this. And here t will be from 0 to 4, since t is the y coordinate. And then the left edge we'll color green. I'll parameterize that as R3. And it will be almost the same as R2. As you can see, it's just a reflection. So it's going to be the same, but with an x-coordinate being negative. Okay, so that's step 2. We've parameterized the boundary and we've broken it into 3 pieces. We could have broken it into just 2, but as I said, I've worked this problem out in advance, and I think that this is the easiest way. So let's move on to step 3. I said in step 3 we will take these parameterizations in and plug them into the original function. So let's stick to our color code. So for R1, if I plug this parameterization in for x and y, so x is t and y is 0, it becomes very simple, just t squared minus 4. Now let's do the second one. For x we plug in the square root of 16 minus t squared, and for y we plug in t. Now if you plug this in and simplify everything, you'll get 12 minus 32t plus 7t squared. And actually it's not too hard to see that for R3 you actually get the same thing. The reason is that in the original function, the only time that x appears is here in this term with x squared. So if the only difference is that the x-coordinate is negative, squaring it isn't going to make a difference. Okay. So let's start step 4 over here. Step 4 is almost our final step. We need to take these functions of one variable and find the critical points of these. So, for the first one, if we take the derivative of this, we just get 2t. So we get one critical point at t equals 0, which corresponds to the point 0, 0. For the red one, we need to take the derivative of this parameterization, and we can see that that's 14t minus 32, which, if we factor 7t minus 16 times 2. So we get one critical point at t equals 16 over 7. And it's not too hard to see, I won't write it out. For the green one, the function was the same. So we also get the critical point at t equals 16 over 7 for the third part. And we'll just have its x-coordinate will be the negative of the one that we got in the red part. And if you actually compute what this is, the point that we get is 4 over 7 times the square root of 33, comma 16 over 7. And so here, it's the same thing, but with negative x-coordinate. So there's only one thing left to do, which I guess would be step 5, but I didn't number it. We need to list all of our points, and evaluate them, and just see which one is the biggest and which one's the smallest. So the first point we found, back up in step 1, we found this interior critical point, 0, 2. And if we plug that into the function, we'll get negative 36. For our first point on the boundary, for the bottom, we got 0, 0 as a critical point when we parameterized that bottom segment. If we plug that in, we get negative 4. And on the circular arc, we got these 2 points. 4/7 times root 33, comma 16 over 7. And the same thing, but with negative x-coordinate. And if you plug either of these into the function, you get negative 172 over 7, which is approximately negative 24.6. And there's one thing we should still be careful about. We should also plug in the boundary points of the boundary components. What do I mean by that? Well, when we parameterized this blue segment, there's these 2 boundary points here. So technically we should plug those 2 points in as well and try them. And likewise, on the red and green segment, this was a boundary component, since that's where each of our parameterizations ended. So really, we should try those points as well and give them a shot at being the maximum or minimum. So those points would be negative 4, 0, 4, 0, and 0, 4. Now for the first two, if x is either 4 or negative 4, and y is 0, then we just get x squared is 16 minus 4. We'll get 12 for either of these. And for the last one, if x is 0 and y is 4, then we'll get 8y squared minus 32y minus 4 is negative 4. So now we just compare everything. And we see that the absolute or global minimum is here. The smallest value that we see is negative 36. So this is the global minimum. And what is the largest value we see? It's 12. Since it's in fact the only positive number that appears. And so the global maximum appears at two different points, at negative 4, 0, and 4, 0.